You know, we can produce all sorts of angles within circles using chords and radii and so forth. And it turns out that there's so much structure to the symmetry of the circle that we can actually gain a great deal of insight about these various angles. Let's talk about inscribed angles. Now, first of all, what's an inscribed angle? Here's one version of an inscribed angle. It basically is just taking two chords that actually share an endpoint in common. And the angle that's actually between those two chords is called the inscribed angle. Let me show you a few examples. So here's an example. Here's another example. Again, you see two chords. They share the same endpoint. And this angle right here is called the inscribed angle. Let me show you another example. Here again, you see two chords. They share a point in common endpoint, and you can see that this angle right here is an inscribed angle. So you can notice a couple of things. First of all, it's okay to have one of the chords actually be a diameter. That's completely fine. Remember, a diameter is a very special example of a chord. It's okay for the two chords to contain the center of the circle actually inside of that angle. That's fine. Or not. In fact, they could actually, sort of have the center be off on the side. Any configuration of that kind is completely allowable. Now, here's a question. How can we find the measure of the inscribed angle? Well, again, the circle is so spectacular that it wouldn't have it any other way but to have the formula be really beautiful. This angle measure is somehow connected to this measure of this arc. And what is the answer? The answer is given by the inscribed angles theorem, which says that the measure of the inscribed angle is 1/2 the measure of the arc. So if you find the measure of this arc and take half of it, you actually get the measure of this angle. If you take the measure of this arc and take half of it, you get the measure of this angle. If you take the measure of this arc and take half of it, you get the measure of this angle. It's absolutely amazing. What a beautiful, beautiful theorem. Let's take a look at some examples where you can see this theorem really proving its true colors. So here's a neat picture. Got a circle, got a whole bunch of chords. Let's have some fun. We're given that the measure of this arc is 80 degrees. Remember, the measure of an arc is given in terms of degrees. Okay? We're also given that this inscribed angle formed by this chord and that chord is equal to 50 degrees. And our mission, should we choose to accept it, is to find the measure of angle CDB. CDB. So that's this measure right here, this angle right here. But that's really easy, because you can see that actually is the inscribed angle associated with this arc. Well, since this is 80, we can actually figure out what the measure of this angle is. It's just half of 80. Half of 80 is 40 degrees. Isn't this cool? I mean, it's so beautiful. There it is. That's 80. This is 40. Bang. Okay. Now, we're told that this angle has a measure of 50 degrees, and our final challenge is to find the measure of the arc AD. AD. We want to find the measure of this arc. What would it be? Well, wait a minute. We have this formula. This is an inscribed angle for these two chords. And since that's 50, and that's going to be half of the measure of this arc, then what must the measure of this arc be? 2 times 50, or 100. So this equals 100 degrees, and this we saw equals 40 degrees. It really is a beautiful result that allows us to quickly connect angles with arcs. Absolutely beautiful. I love it. Circles are great.